Hello, today continuing the topic of chemical reactions and equations, we once again learn how to balance coefficients and make use of the method of least common multiple in order to achieve proper balancing. Alright, let's focus on some other chemical equations today and choose a displacement reaction as our topic. So for instance, if we consider the interaction between sodium oxide and let's say hydrochloric acid as an example, it becomes apparent that in the course of this reaction, sodium chloride is formed as a product, and as a result, water is also present. As part of the instructional assistance in this regard, we can set up a framework specifically to guide the reaction equation, so that you can then write such equations yourself. Please take a look at everything that's left outside. It all comes together in one formula. And the formula is created according to the rules of the zero-sum method for ionic compounds. And inside, the remaining hydrogen and Kester rod will always be water. Okay, this is the exchange reaction. Look, we're going to start here with whoever has the higher index, but in exchange reactions, in my opinion, it is better to adhere to some additional tactics. Let's observe how it operates, all right? Initially, in terms of equalizing, we are going to equalize the level of sodium. Secondly, chlorine, which is beyond the boundaries. Thus, it transpires initially the elements are beyond the boundaries. At this moment, the subsequent stage will entail the balancing of hydrogen. Finally, we will tackle the oxygen element. In my opinion, it is very convenient because then you will not make an error in the sequence of the equation. And let me tell you, we have some really challenging equations here. So it is like we are going from left to right, and then we return back from right to left. All right, let's start with sodium. His index is the highest in this case, and he comes first in terms of equations. On the left side 2, on the right 1. The multiplier for sodium, let's emphasize it, is 2. We divide 2 by 2. In the first step, we do not write 1. Instead, we divide 2 by 1, and the result is 2. They put a coefficient of 2 in front of sodium hypochlorite. Next, we'll be balancing the chlorine element. We've got chlorine on the left, 1, and we've got chlorine on the right. Let's take a look. Now it's already 2. The multiplier for chlorine is 2. 2 divided by 1 equals 2. No changes there. And 2 divided by 1, the 2 is still intact. Moving on to hydrogen. We have 2 hydrogens on the left and another 2 hydrogens on the right side of the equation. Hydrogen on equal terms. And finally, let's balance the oxygen. On the left side, there is 1 oxygen, and on the right side, there is 1 oxygen. So we have a double for hydrogen, chlorine, and sodium, but for oxygen, we only have a single one, unlike the other elements which have 2 each. The equation is set equal. So it turns out that the equation sodium 2O plus 2H chlorine equals 2H chlorine and H2O. Let's provide an example of another reaction, shall we? I will write down the exchange below, but I am going to stick to the same rules we just talked about. Okay, we will examine the interaction between aluminum hydroxide and H2SO4, which is sulfuric acid, as an example to illustrate the chemical reaction between these substances. We are currently undergoing a reaction that resembles an exchange. As a consequence of this reaction, you obtain aluminum 2SO4 salt 3 times, and within the framework, there is a presence of hydrogen and oxygen, which combine together to form water. All right, now let's start leveling the playing field. Now listen up. In this case, this tactic of leveling really helps. Aluminum on the left 1, aluminum on the right 2. Put a 2 in front of the aluminum formula H3. Now we can calculate 1 as a whole piece on the left of SO4 and 3 on the right. Thus, we put a 3 in front of H2 and SO4. Now let's discuss hydrogen. Be cautious. 3 hydrogen atoms on the left, 2 on the right, 6 in total. And also 6, 12. And on his right there are 2. So before the water formula there would be a coefficient of 6. So we end up with 6 oxygen here and another 12. Total of 18. And on the right side we have a sum of 12 plus 6, which gives us a total of 18. In such complex equations, in my opinion, it is very convenient to double check. On the left side, we have the element aluminum, which is equal to 2. On the right side, we also have the element aluminum, which is also equal to 2. Following that is the subsequent gray. After that, this particular item on our left side has a value of 3, and on the right side, it is also revealed to be 3. Moving forward, we have a combined total of 12 hydrogen atoms on the left-hand side, and we also ultimately obtain 12 hydrogen atoms on the right-hand side. And oxygen, finally, there is an abundance of it in this location, as we have 18 units on the left side and 18 units on the right side as well. So in exchange reactions, and these reactions can be incredibly complex, judging by the examples I demonstrated, you must work with great care and preferably adhere to a well-thought-out strategy in order to achieve the desired outcomes. As an additional interaction, not merely a reaction of exchange, let's demonstrate another combustion equation. Burning is a chemical process that happens when substances combine with oxygen in a reaction. Let's say we take propane, and the reaction goes with oxygen. During this reaction, carbon dioxide is released when fully burned and water is released. However, when it comes to the burning reaction, we recommend following a specific scheme, even though we initially begin with the element whose index is greater. But in my opinion, it's convenient to use the sequence of equalization here. So pay attention. Initially, we're going to equalize the element that is the first in our intricate compound. This is carbon. There are 3 carbons on the left and 1 on the right. The multiple for carbon will be 3. So we divide 3 by 3, which is 1. And here, accordingly, we divide 3 by 1, which gives us 3. Carbon is equal. Hydrogen on the left side, it's our second in terms of balancing. On the left, he's got 8. On the right, he's got 2. So between 8 and 2, a multiple of 8, when we divide 8 by 8, the unit remains. When we divide 8 by 2, we put a 4 here before the formula for water. Carbon, hydrogen balanced out, and oxygen remained. Oxygen on the right side, 2 on the left, and on the right side, if you can't see it, you can write it like this. Here we have 6 oxygen and plus 4 oxygen, so this is our oxygen. He is the third person in our line of succession, just so we do not get confused. Let us proceed with the show. And then, in total, there will be a total of 10 oxygen atoms. We divide 10 by 2 and get a coefficient of 5 here.
Our equation turns out to have the form C3H8 plus 5O2 is equal to 3CO2 plus 4H2O.
However, on occasion, there can be complications in the burning reaction. Allow us to demonstrate the process. For example, we can take the substance C2H6. This substance is called ethane plus oxygen. When it burns completely, carbon dioxide and water vapor are formed. Let's begin leveling, but let's adhere to the tactics in this situation. First item, second item, third when equating. Let's start with carbon. 2 carbons on the left side, 1 carbon on the right side. So prior to the CO2 formula, we established the coefficient as 2. Carbon is equal. Proceed. There are 6 hydrogens on the left side and 2 on the right side. Then we will put a coefficient of 3 in front of the water formula. Following that, we need to ensure a balanced distribution of oxygen. Oxygen should be given the utmost priority as it is our final concern. And here we can see oxygen 2, and on the right side there are a total of 4 oxygen atoms and an additional 3 oxygen atoms that make a total of 7 oxygen atoms in this compound. However, the total number of oxygen atoms is 7, indicating that each molecule contains 2 oxygen atoms. Therefore, on the right side of the equation there are 7 oxygen atoms. Dividing 7 by 2 yields a fractional value of 3 and 5. However, due to the restriction on fractional values and the requirement for all coefficients to be integers, we need to multiply all the given coefficients by a factor of 2 in this particular case. Then we'll put a coefficient of 2 in front of C2H6, a coefficient of 7 in front of O2, giving us a coefficient of 7. Before CO2, we'll cross out 2, so it's 4. Before crossing out H2O3, we get 6. Let's rewrite the equation so it's easy to see. So in the end, 22H6 plus 7O2. Thus, it is discovered that the chemical equation consists of 4 molecules of CO2 and an additional 6 molecules of H2O. In such complex equations, you gotta make sure to double check, especially. I think it's definitely necessary to do this so that you can be sure whether you did everything right or not. Okay, let's check it out. Left side. We have carbon on the left side, twice 2, 4. Let's examine it closely to see what we find. So on the right side, it turns out that we also have a total of 4 carbon atoms present in the compound structure. The equality of hydrogen on the left side is 6 multiplied by 2, 12. Calculate the product of 6 multiplied by 2 on the right side, which equals 12. And now we simply need to double check the oxygen levels. The result of dividing 7 by 2 is 14 oxygen atoms. On the right side, it is revealed that 8 plus 6 also equals 14. All right, our equation has been equated. However, as you can see, equations possess the ability to be both relatively simple and complex in nature. But in all of these chemical reactions, we have been using the same method. He is called the least common multiple method. I just provided you with an additional tactical maneuver, where in return reactions are carried out in a sequential manner and, for instance, similar to the way they are done in combustion reactions. But I think you'll agree with me that the most challenging in terms of balancing are definitely combustion reactions. By trial and error, you know, there can be even more complicated interactions than what I showed. But I really hope you understand. That's all for today. Goodbye.